heard a few complaints about the homework problems. So I'm wondering, how do you feel those problems? Are they too hard or too taking too much time to finish? So is it because like the problem is too hard or the problem is too many?
Too many.
So so basically about work amount rather than hardness. Or mixture. Mixture. Okay. So how many of you think the problems are too hard? Just one. Okay. And how many? Okay. How many of you think the problems are too many, too much, or below? Okay. Well, honestly, I maintain the same level of the work amount for the entry level machine. So for entry level machine, of course, the analytic problems usually maintain about around 10. So but anyway, this problems I know is harder than like those entry level problems. But anyway, given I heard the complaints, and because I want to serve you and I want to torture you as well, I'm gonna make a survey and to investigate what's your opinions, what's your feelings about these problems. I also want to know what's the issue, right? It's because some necessary knowledge, you're not familiar with, like matrix or vector derivatives, linear algebra. You still need time to review or learn, or just because those problems are like hard. And then probably I will make some adjustment. And one possible strategy is to maintain a number of problems, but I will put half of them to be like bonus problems. So that will still work for those ambitious students who want to get like, more grades, right? But probably at the same time will make many others like easier and better. But again, as I emphasized at the very beginning, I repeated like 1,000 times or 1,000,000 times that this course is not a trivial course. It's a graduate level, and it's mathematically intensive and also requires non-trivial programming, and you will see later. And you definitely, if you really want to learn something from this course, you definitely need to spend some time after class. Don't count on me in every detail. Because you are grad students, I assume that you have some capability to do the self-study. So at least I suggest after you follow me in the lecture, try to derive those results for yourself. Then you won't have any question for most of the homework questions, because the tricks to solve those problems are already in our lecture. But if you do not follow what I have derived in the lecture, you feel like strange, unfamiliar, uncomfortable, or sick of it. So yeah, and again, I don't know how many these things I repeat, but again, any problems, any issues, and questions, and any strange feeling, uncomfortable feelings, feel free to come to the office hour, complain in front of me, and don't hide it inside. And any questions so far? So I will give the fewer problems on homework 3, because you need to submit midterm report before the fall break, and also need to finish the homework 2, 1012. Yeah. So the work amount of homework 2 will be significantly reduced, but probably will still higher than your expectation. But anyway, I'll look at the survey results and make the corresponding adjustment.
And then will those be more towards the coding side rather than theoretical side?
Yeah, because in the past few weeks, we're like trying to go through all the necessary knowledge for us to build up a fancy probabilistic models, and later, because we're right now on stage 2, we're going to look at those classical widely used probabilistic models, and you're definitely required to implement those models. So this is not some models on papers. You have to convert them into code. Does that make sense? At the same time, the amount of analytical problems the number of analytical problems will be reduced. But you might spend a lot of time debugging code. So please prepare for this big shift. Okay. So let us continue with the generalized linear models. So in the last lecture, we introduced the linear model for regression, right? But we emphasize that we're not talking about basic linear regression. That means you just linearly combine all the original features. We want you to do some pre-processing step. We call like the nonlinear basis functions, right? So whatever original feature vectors you have, you can come out some like m nonlinear basis functions, and for each basis function, the input will be the whole original feature vector, but output will be one feature, which is kind of nonlinear to the original features. And then our linear regression model is based on some transformed nonlinear feature vectors. That means even you apply some nonlinear model or linear model on that, overall it's still a nonlinear model. It preserves the flexibility to model complicated relationship between your input and the output responses, right? So then we talk about how do we conform, how do we do the maximal likelihood estimation, and we talk about the overfitting issue in the polynomial regression case, right? So actually, the highest order of polynomial really matters. Right? So the higher the order you choose, the more likely you will overfit data, meaning that you can reduce the number, you can reduce the training error to 0. At the same time, you have like a big jump in your test error. Right? So one strategy to overcome this overfitting problem is to regularize the feature weights. Right? So I have observed that the higher order polynomials you incorporate, the larger the corresponding weights you will have, right? So obviously, because the weights are too large, one perturbation of the inputs will incur like extremely large, extremely different outputs, right? So you can imagine test performance will be very bad. So an intuitive idea is to shrink the absolute value of the weights. Unless it is highly supported by data, I just want to encourage the feature weights to be as small as possible. That means we need to introduce, in front of the original objective function, we need to introduce some term. It's called regularizer, right? So this is in general how we define a regularizer. We can add a summation over the absolute value of each feature weight to the power of q. So q must be positive. And if we use q to be 2, that returns to our commonly used like L2 regularizer, sometimes called. It's just to calculate the L2 norm of the weights. But if you choose q to be 1, that's even more famous. It's called Lasso L1 regularizer. It can guarantee that some of the weights which are like prompt are directly shrink to 0. So as to why it can be directly shrink to 0, it will be, I'll not cover in this course, but if you're interested, we can discuss. And there are also other processes of q, but the most commonly used are q equals to 1 and 2. You can choose q equals to 1.5. You can choose q equals to 0.5. No one will blame you, but you should give a reasonable reason. But these are not actually not what we want, right? Not always what we want, right? Because we are Bayesian, right? At least in this class, you need to pretend to be Bayesian. That means we need to consider the posterior distribution, the distribution rather than point estimation. So we call this model, it's called Bayesian linear regression, because we want to emphasize Bayesian perspective in this model. How can we do that? We first assign a prior over the feature weight vector. So naturally, this is a common choice. And don't ask me why, but this is a very, very common choice, that we assign a Gaussian prior over the weight vector. And the prior, obviously, is determined by a mean vector and a covariance matrix, M0 and S0, right? And then given the mean vector, we sample the observed response P through this another Gaussian, right? And the mean will be the design matrix Y multiplying with W, right? And we assume the observed response are corrupted by some noise. That's why we allow some inverse variance or precision beta here, right? And given the prior likelihood, this is prior. This is prior is likelihood. Naturally, we want to combine them to get the posterior distribution. That is the posterior distribution of the feature weight vector after we have observed those training data, right? So because you multiply one Gaussian with another Gaussian into the normalization, you will definitely end up with a third Gaussian. So I highly recommend you to do that. Although it's kind of tedious, but it is. And here is the posterior mean and posterior precision. This is the inverse of the covariance. So if you want to compute the covariance, you just take inverse on the right hand side. Right? So again, I want to encourage you to derive this, figure this out. So the trick is exactly the same when we derive the conditional Gaussian and marginal Gaussian, just completing the squares. So this is the most general case that you can assume you have like a dense covariance matrix in the prior and a non-zero mean vector in the prior, right? But in practice, we often make a simple choice. We just assume, okay, the prior mean is 0, and the prior covariance is just a diagonal matrix determined by a scalar alpha. We call alpha is a precision parameter because we take inverse and multiply with the identity matrix, right? And then again, we just substitute 0 and alpha inverse I for M0 and S0 here, and we use this template to compute posterior mean and the covariance, and now with this result. So now I want to show you how, when we use Bayesian framework to model the training procedure, we look at more and more observations, how the posterior distribution will change and vary. Right? So to give you a sense on that. So here are 3 columns. Well, the first column just represents the likelihood function. So likelihood function in terms of the weights. So suppose we only have 2 weights, W1, W0, and W1, intercept and weight for X. Right? So this just represents how the likelihood function in terms of the weights, W0 and W1. So Y and X are some observed data points. So don't confuse here. They do not vary along with X, Y. We just assume some X and Y pair is observed. And I want to look at how this likelihood function, so this is a function of W, varies across the region for W0 and W1. Does it make sense? And the second row represents the distribution of W. So if we have no data observed, we only have a prior distribution, right? But we have observed the data one by one, then we're going to update our distribution of the weights to end up with different posterior distributions. Right? And third one is the view from the data space, meaning that given the prior of posterior distribution here, I just use that distribution to sample a bunch of instances for W. Right? So given HW, the relationship between y and x is determined, right? Because y is assumed to be W0 plus W1x. So it's essentially a line, right? So each W instance will correspond to one line. Of course, I can sample a lot of instances for W from those posteriors, then we'll end up with different lines, right? We want to see how those lines cross the space in the data space. Okay. So just keep those settings in mind, right? So at the very beginning, when we do not have any observations, we only have the prior, right? So the prior, you can imagine, is oh, by the way, I have to explain what the color represents, right? So the color is the more the color towards the dark blue, the smaller the value of the density or the electrical function values. Or the more the color toward the dark red, the larger the value. Okay, so if you mean like something like a light green or yellow, it's just in between. So keep it in mind. And then let us look at the very beginning, we do not have any observations. So this is for the first line, first row, and we see we have like a big wire, right? This black wire that crosses a large range, meaning that okay, it's possible W is sampled from every point, every position, right? And then we can sample W from this prior distribution, and we can sample a lot of points of W, a lot of instances of W. Each W determines a line. We can see the positions of the distributions of those lines are kind of diverse, right? Now, things got changed. So now, suppose we have observed the first data point. Right? So remember, although in our probabilistic model, we assume W is kind of random, right? We have a prior distribution, posterior distribution, but to generate data, we must have some deterministic value for W0 and W1. So those white crosses represent the true value, the ground truth value of W0 and W1. And we want to use our probabilistic models and to infer this ground truth. And now, after we have observed the first data point, say x1, y1, right? We can check the likelihood function with respect to W. Remember, x1, y1 here, they are fixed. And then we just look at when we vary the values of W1 and W0, how does this likelihood function change, right? So what can we observe? So we can observe that, okay, if your points for W1, W0 are quite far away from the ground truth, like here and here, the likelihood function value is pretty small, right? And the larger value of likelihood function is concentrated on some line which is close to the ground truth, right? So now you can see the usage of likelihood function. It actually constrain the range of your the usage of the data points. It actually constrain the range of your likelihood function, right? So this is the likelihood function. And now if you multiply the prior with the likelihood function, so you multiply here and here, you normalize your now.
So what's this gradient of that region that it makes certain angle and then for the next point it changes?
Gradient what?
Red region. Can you see
here?
Yeah. So initially it was the spread all around the region from -1 to +1, and then we find that it's pretty much focused around that original point we observed. region has got a net, right? Is that anyway meaningful? Because it keeps on changing from one point, from first to the second and from second to the third.
Oh, you mean why the high likelihood value regions exactly. Like this, right?
Yeah.
That depends on the form of likelihood function. You cannot expect your likelihood function will make the largest value to be concentrated on this. This is very hard. So I mean, actually, different x1, y1, you will say they have a different lines, which have the largest values, right? But actually, you're gonna like combine a bunch of likelihood functions, given a bunch of x1, y1. So when you synergize them together, you get estimate you're getting close to the ground truth.
So you need to say that the likelihood distribution is going to govern that how that.
Yeah, it will definitely will govern how your posterior distribution will change, but it cannot, like one single likelihood cannot give you the right answer. It just gives you a part. You know, a lot of it's kind of cross-outs, right? One people help doing that, another point help doing that, another point help. You synergize them together, you get optimal choice. You cannot expect that one likelihood function can tell you the answer. It's not possible. Any question?
So for the likelihood match and the 20th point, is the match from the almost the sum of the 20 points or only the 20th point?
20th point. This is 20th point. So let us first start with first point. You don't need to jump to the 20th point. Yeah. So when you multiply this likelihood with the prior, you end up with a posterior, right? This is the posterior distribution after you have observed the first data point. So what we have observed that we have a dramatic change in the distribution of the weight W0 and W1, right? So, but obviously, the high density regions of this posterior distribution becomes much smaller, right? I mean, it's contrast. It contrasts a smaller region. That's reasonable, because at the beginning, like you have like you have the biggest uncertainty about those parameters, right? After you have observed one data points, those information incorporated from this data point will help you reduce the uncertainty. Will give you a better guess about the ground truth, right? Mm-hmm.
So you basically take the prior estimate in the previous iteration and get the product with the latest likelihood, and then you generate this next prior, right? Or you would say that the posterior.
Yeah.
Or that's it, right?
Yeah. And then we use this posterior distribution. That is the posterior distribution after observing only one data point, right? To sample W0, W1. In sample all the points, remember we just mentioned that one particular instance of W0 and W1 will determine one point, one line, right, in the data space. So when you sample them, you will sample a lot. Now you see the distribution of those lines in the data space. How does it compare with the last case, the previous case? It is narrow as well, right? Why? Because your posterior distribution becomes more informative, more contracted. So you can imagine the sample W, the region of the sample W will be smaller. That means your corresponding data functions, data lines will be narrow as well. Right?
So when you're sampling the W1 and W0, is it true that the red region W's are more likely to be selected?
Of course.
Okay, another question is about the likelihood. What the likelihood density looks like a belt?
That depends on the likelihood itself. That depends on likelihood itself. So different likelihood will have different shapes, right? Yeah. So here, because this likelihood is, you can imagine this is what? Yeah, this is a Gaussian, right? Gaussian of y given W0 plus W1 x plus some beta inverse, right? So this is a linear function here, although you take the exponential of that. So that's what we have observed after first, after dealing with the first data point, right? And then when we look at the second data point, so here the likelihood function for the second data point, it looks like this. So see, this likelihood function is different from this likelihood function. So they are not necessary to be aligned everywhere. Okay? But when you multiply this with this, or you multiply this too with this, the same thing, you get the posterior distribution after you have observed 2 data points. So now we can say the high density regions are reduced even more, right? It's more concentrated, much more concentrated. And at the same time, so this blue circles represents the 2 observed data points. So now if you use this posterior distribution to sample a variety of W0.1 values, and each instance of W0.1 determines 1 lines, you collect those bunch of lines, you will see they're even more concentrated, right? And you can see roughly they're consistent with the observations, right? We can keep doing that until we have observed the 20 data points. And so this likelihood function is a likelihood function for the 20 data point. Given 20 data point, don't be confused here. It's just one single likelihood function. I mean, likelihood function for a single data point. Right? But when you multiply this with the posterior distribution right before, you end up with this posterior distribution. So it's kind of like concentrated to a single point, right? You can see the trend. And if you use this posterior distribution to sample the W0 and W1, you sample log, you found, okay, all those lines are kind of overlapping, right? And those lines are highly aligned with the points we have observed. So now you can see how the posterior distribution are updated and changed when we see more and more data. So at the beginning, we have like the largest uncertainty, so we have a flat wire. But when we observe more and more data, and our uncertainty about the parameters keep decreasing, right? And there's this like Bayesian version of the large loss number. It can tell you that posterior, it's called posterior consistency. It can tell you that when you have like infinite number of the data points, in many cases, the variance, the posterior variance, will converge to 0. So it converges to a single point, right? So this is consistent with like classical large numbers law in the frequentist world. So, of course, in the Bayesian linear, in the world of Bayesian linear regression, we can also apply some regularization trick. But in this framework, the regularization term now turns to a prior. You see, the term prior. Why? Because when you do the maximum likelihood estimation, we take logarithm over this prior. You see, logarithm cancel EXP, right? You end up with the regularization term we have seen before. So this is there is correspondence between the regularization term and the prior for your linear regression model. So when you take Q here equals to 1, so our prior is proportional to the exponential of this summation of absolute values, right? So this is called Laplace prior. If Q is taken to be 2, then it corresponds to Gaussian prior, which is equivalent to L2 regularization if we both do the map estimation. Okay? Any questions so far?
Is there any chance that after you observe more data, get more undeterminate?
That depends on the assumption of your data. If your data is like, for example, if your data is not IID, then no one can tell you how the posterior variance will change.
But you need to go back to, yeah. My question is that is there any possibility that after you observe more data, at that point not diminish, rather it grows?
It is possible.
It is possible.
It is possible. But for this simple case, it won't be possible.
Okay.
I mean, if numbers, you have to assume. You have to assume. You have to assume like at least they are ID. Right? If they are not ID, then how do you prove that? You can follow the proof. You can imagine like if my samples do not give you any information, just random noise. No matter what or how many data you have received, it won't like reduce the uncertainty.
I find the last pile and golden pile is the fourth member of the exponential family. This is a connection with that.
With what?
Here the cube, when it's one Laplacian pile. Laplacian distribution is a member of the exponential family. And when cube equals 2 is also a exponential family.
Yeah, this is exponential family. So
when the cube become other members, like 0 or 3, or this also have the same conclusion.
yeah, why not? So remember, what is a natural parameter and which is why used to represent sufficient statistics? Only UW, right? So this is obviously an inner product, right? You can simply define UW equals to like W1 to the power of Q, W2 to the power of Q, W the n to the power of Q, right? So and beta is half or whatever. Yeah, that's a good question because I always try to like make connection between what I have discussed here and what I have talked before. Any other question?
What is the advantage of Bayesian linear regression over the ordinary square linear regression?
So, as we just mentioned, we care about posterior distribution, right?
Right.
We can always look at the posterior distribution of the weak vector, but if you use like ordinary listed regression, least square problem, what you get is maximal likelihood estimation. We just got 1 point.
Yeah, but in that case, we can calculate the confidence intervals as well.
Yeah, you can calculate confidence intervals. That's another way to quantify uncertainty. So what's the point?
I want to know if there is an advantage of using this one over the OLS linear regression.
Oh, for this particular case, yeah, there seems not like a significant advantage. But imagine that if you add a variety of pairs, you have the posterior distribution, all the posterior distribution you'll have, right? So you can ask any probabilistic questions, right? Not only like confidence intervals. Suppose I want to ask you, what is the chance that your weights, I mean, after looking at 3 observations, the weights is the square of the weights is between 0 and 1.5. How do you answer this question? If you use Gaussian distribution, it's very easy. Right? But if you use confidence intervals, you need to justify because your statistics change, right? And you have to assume another hypothesis testing. But in general, like posterior distribution give you all the information you require. You can safely use that to do whatever you want. To me, it's much more better. Any other question? Okay. So a second benefit, I will tell you. Actually, we discussed before. We said, okay, if we use Bayesian framework to do the prediction, we're able to integrate all kinds of prediction results to make your prediction more robust, right? So how can we do that? We use the predictive distribution. So the predictive distribution is different from the posterior distribution of the model parameters, namely weights. Instead, we want to know, given the training observations t, for arbitrary test point t, what is the distribution? This distribution does not contain W, the feature weight vector. The question is how can we arrive at this distribution, right? So basically, it's just you use the posterior distribution of the feature weight vector W to sample all kinds of W's, all possible W's. And for each W, you use that to make a prediction. And then you average up all the predictions. You get the predicted distribution of the test sample given the training data T. This is bounded T. So it can also be written as an expectation under the posterior distribution of our model weights. The expectation of what? The expectation of your prediction. Does it make sense? So what's the benefit for us to compute the predicted distribution? You actually integrate all the possible predictions, right? You go over all possible W's. And each W will make a prediction, and your prediction is weighted by the posterior distribution. Obviously, the W's which take the high density in the posterior distribution, their results will be weighted more, right? But at the same time, I also average over those small chunks, W's with results with W for small chances. In this way, we integrate all kinds of prediction. We can expect our prediction will be more robust.
So with this distribution, it's the probability of a future data point given data.
Yep. Yep. So this mobility represents all the past data we have observed. Right? Those scalar T is the test data point, any future point you want to know, right? So suppose you are giving like a new test point X star, you want to know what's the distribution of T star given you have observed the trained data T. This is called predictive distribution.
And is it just for one point, or could you?
Yeah, you can spend it for any points.
Like a data set.
Yeah, you can do it for data set.
If this distribution has any connection to the Gaussian process, and the Gaussian process is also using the observation, and you
the prediction of Gaussian process can be put in this predictive distribution framework. This is kind of one instance. Everyone is comfortable? All feels strange? Is it really strange? But here is something unique for Bayesian framework. Right? If you use map estimation, you can only pick up one optimal W. Use that W to make prediction, right? But if you have a posterior distribution, you're gonna average all possible predictions, weighted by the posterior distribution. Right? So in our linear regression case, Bayesian linear regression case, this prediction is fulfilled by this Gaussian distribution, right? And the posterior distribution is computed from here. So again, we can see the likelihood or the prediction is a Gaussian, right? The posterior is a Gaussian. That means that when you multiply together, we will integrate out, normalize it, we still get a Gaussian distribution. So that's benefit of Bayesian linear regression. It's kind of convenient because everything is Gaussian. But it represents different meanings. So predictive distribution only represents the interested response or interested output given the observed data. We integrate out or we marginalize out the effects of all possible feature weights. This is called predictive distribution. It's mainly used in prediction. But the posterior distribution of the model parameters, that is what we just mentioned, is here. This is the posterior distribution of the model parameters. This represents that, okay, after I have observed the data T here, what will be the posterior distribution of the model weights? but they haven't been used for prediction. If I want to use for prediction, the ideal way is to use that to calculate predictive distribution. Okay. Hopefully, no one will be confused at this point. And then we can look at how the predictive distribution varies when we observe more and more data sets. So suppose our ground truth is a sine function. So this is a green line is a sine function. It's a ground truth. And we have observed only one data point. That means our training data is only upside y. And then I can use that framework to compute the predictive distribution. So for any x, I can compute the distribution of the corresponding y, right? And those shaded regions just represent the posterior mean plus or minus one standard deviation. It actually represents the span of the your prediction, because your prediction in Bayesian framework is considered as a random variable. They're sampled from the predictive distribution. So now you can say, first, only one data point is really bad, right? It is far from the ground truth. And second, when your prediction is close to the training data, you say the variance, prediction variance, is much smaller. I'm not saying it's small, but it's much smaller than the prediction on the other locations, right? And if we have observed two data points, this trend here, this trend is more obvious. So first, the mean of the predictive distribution, which is the right line, looks much more reasonable. And then overall, the predictive variance reduces a lot, but it's still quite big, and also quite large when our test points, our test positions is kind of far away from the training points, right? And then again, we observe that the closer the test location to the training data point, the smaller the predictive variance. Okay. And again, when you observe 4 data points, you have an even better looking predictive mean, right? And also reduce the predictive variance. And after you have observed many data points, those blue circles, now we can say the the mean of the predictive distribution is quite close to the ground truth, right? And also we have pretty reasonable predictive variance everywhere. So we can say for the predictive distribution, it also consistent with our intuition. When more and more data are coming in, my predictive distribution will be more and more concentrated. We have less and less uncertainty, and our prediction will be more and more accurate. Any questions so far?
Do you have any guesses on what the behavior looks like after these points? On the last graph?
This one?
Yeah, what do you think it would look like if you went more to the left or more to the right? Like,
it will still increase the predictive variance.
So it will still like flatten out?
Yeah. Okay. Yeah. That's the issue of not only Bayesian linear regression is a kind of problem for all kinds of machine learning problems, because machine learning is good at interpolation but bad at extrapolation. So as to why, I guess we don't have time to explain this philosophical problem. Yeah.
So does that mean only the peak area can be covered by the prediction? Like
you mean here?
Yeah, or like any of the graph. Like, does that mean only the prediction can only predict the peak area?
It's not to say like only. I mean, if you want to get like a good predictive performance or reasonable prediction, you're gonna to ensure that your test point is not far away from the training data. If it is quite far away from training data, it will be like this. You have like a large variance, which indicates that your prediction might not be that accurate. That's the benefit of Bayesian, because I can tell you, I'm not sure about that. Don't trust me. Right? Yeah.
So relating to the previous expression that you saw, so that red line that you have drawn, it basically refers to alpha, that's the mean predictive value, and beta basically indicates the pink region, which is the variance.
Yeah, it depends on alpha beta as well.
So we are basically trying to get a better estimate of alpha and beta, right? With incorporation of more training.
Oh, no. I believe this figure is drawn with fixed alpha beta. You're not like jointly minimizing the objective function with respect to alpha and beta. You just assume alpha and beta are fixed and see how the change of the predictive distribution.
So when you say that, what the pink region basically indicates the variance of the predictive. What do you say that it's the variance of law?
It is the predicted mean plus or minus one standard deviation of the predictive distribution. Does it make sense?
I was just trying to relate to what we saw in the previous slide regarding the distribution.
So this is our predictive distribution, right? This is our predictive distribution. And this red line represents this function. Remember, this is a function. This is different x corresponds to different value of this predicted mean, right? And this is a predicted variance, right? So how is it drawn? You just draw the predicted mean as the red line, and you calculate predicted standard deviation. You plus one standard deviation minus one standard deviation to get this shaded region. Does it make sense?
How do you quantify the predictive distributions and the function distribution? Like in the OPT, you can use the MSE to quantify the error.
So I don't know what's your point. You mean you want to quantify what?
Quantify the error between the predictive distribution and the function distribution. I mean, in the OT, you could use mean square with the metric to see.
Okay, that's a good question, because what we output is kind of distribution, right?
Yeah.
And but if you want to give the prediction, you must pick up one value, right? So remember what we have talked about in the last lecture. The Bayesian decision theory, right? What is decision theory? What is decision? Decision means that whatever posterior distribution you have, you must give one optimal point, right? So we'll talk about on a variety of environments, how do you pick up the best decision to make a prediction, right? So if you use L2 error, then the optimal prediction will be the expectation of the predicted distribution. Right? This is what we have just learned. But if we want to use other metric, then that depends. So with the posterior distribution in your hand, actually you can do whatever you want. For me, I can intuitively just pick up the posterior mean as a prediction. I can tell you it is guaranteed if you use mean square error as your metric. But if you use others, that really depends. Mm-hmm.
So how do we set an optimal initial alpha and beta value?
No, here alpha and beta are fixed.
Right.
I will discuss about how to learn alpha and beta later. And also, that depends. Like alpha beta values, different initial values of alpha and beta may lead to different results. If your objective function is convex, or it doesn't matter. And if your objective function is non-convex, that depends. Any other question? Is everybody comfortable? Someone feel confusing? Well, I want to restate that problem again, right? So, given a predictive distribution, if you in the practice, I want to still give one, right? So you can define all kinds of heuristics. You can pick up the mean. You can pick up the mode as your prediction. That depends. That's not called decision procedure, right? You can choose a rule to make your decision, but if you want to make the optimal decision, as we discussed in the last lecture, you have to follow up some rules, right? Like if you do the classification, right? So most of the classifier only give you a probability, 0.5, 0.6, but you're gonna to output whether it's 1 or 0, right? And in this case, how do you make decision? Probably intuitively, like I will set up threshold to be 0.5, and I decide to report 1 if my classifier reports bigger than 0.5, right? Otherwise I report 0, right? But you can change the threshold. You can change it to 0.6 or 0.8 because I want to say I want to have like a true TFR or FR loss rate or whatever. I forgot the. But it depends. Does it make sense? Okay, we can observe this from another angle. That what does the function look like if we sample W from the posterior distribution? Right? So again, this is very similar to the example we just mentioned. So we use the observed data point to calculate the predicted distribution, to calculate posterior distribution. And then I use posterior distribution to sample different W, right? And then, given one W, I can determine the relationship between Y and X. So it's function of X. So different samples will correspond to different function curves. And as for Y, this is not a line. Remember, we have performed some nonlinear feature transformation. So although we can say, okay, I do some linear structure, linear computation, but the end up is a nonlinear function, right? And then we can say, if we only observe one data point, and we calculate I calculate posterior distribution, I sample a bunch of W, and then when I look at the function curve in the data space, I found it's quite diverse, right? And when we look at 2 data points, it is more concentrated. It will look like 4 data points, it's even more concentrated. Now, if we look at many data points, you can see it's quite consistent, right? Quite consistent with the ground truth, which is green sine curve. Just a few examples for you to give you a sense about the Bayesian inference procedure. It's called Bayesian inference. So any questions so far?
Does the prior distribution matter in this case, or are we just concerned with those two?
Right now, for all those results are based on posterior. But to calculate posterior, as well as the predicted distribution, you have to take into account the prior. Imagine that if I have like a very concentrated prior, of course the posterior might be even more concentrated, right? Or you have like weird or like it's concentrated on a raw case. And now you have a likelihood where the ground truth is in another place. So that actually gives you a like bad effect, right? Those are all very interesting. So yeah, probably I will ask you guys to implement a piece of code to look at, examine different priors. Okay, let us look at the Bayesian model comparison. Suppose we want to compare a set of models. So I have a arrow models. Oops. Okay, I found switch to the PPT. So while I'm switching to the PPT, any question, feel free to ask. Regarding the figures we just mentioned or any other things. How many of you have started homework 1? Oh, really? Okay, I do not care about this hour Monday, right? So I need to charge well, and then we can go back to the. We can show derive something. Sorry for the run out of battery. Okay. So suppose we have a set of models. We have L models. Well, those models can be determined by different hyperparameters. And the data is generated by one model, which we're not sure. So you can assume in prior, we have some uncertainty about the model the God used to generate data, right? So we can assign some prior on the model. And then given the training data, we wish to evaluate the posterior distribution of using that model to generate data. So this is similar to like a standard Bayes rule to compute the posterior distribution of using model I given the data is proportional to the prior of using model I multiplying the likelihood of the data given the model, namely the probability that the data is generated by MI. So this part, the probability of the data given model MI is called model evidence. So sometimes we want to compare which model is better, which model is wrong, right? Which model is better, which model is worse. We introduce a so-called Bayes factor. When we do that, we just compare whose model evidence is larger, right? This is like maximum likelihood estimation, right? How do I identify a model? I want to find out the model under which the observed samples has the largest chance to be generated. This is the same thing. I just compare with the evidence of different models and calculate this ratio. And the bigger one will end up with a better model, right? And another idea is that, like now that I have a bunch of models, why not we just average all the models' prediction results to get even better results? So this is like a predictive distribution, right? I want to average all possible outputs to give more robust results. So we apply it in like multiple model cases, the same thing, right? And we just do this average, and we use each model to predict the output and weight it by the posterior distribution of using that model. Right? And the model selection is actually not to average models. It actually choose the most probable model alone to make a prediction. So that's actually very important in practice, because like I always can have a bunch of models, right? I want to know whether I should use neural nets or use logistic regression is more than enough, or I should use support vector machines, right? And how do we do that? How do we choose that? And we can compare with the model evidence as well. To illustrate this point, we need some qualitative analysis. We need to first give a crude approximation of the model evidence. So basically, we assume the posterior is centered around its mode, and the prior is flat, meaning that, okay, I have this flat prior, and it's kind of uniform. This is a very, very oversimplified assumption. It's just to reflect some properties. And the posterior is centered around its mode, meaning that it's centered around its map estimation, and the range is much smaller, right? So this is the reason for under like large data, because as we previously seen, when more and more data come in, your posterior distribution is contracted more and more, right? It's this high density region is compressed into a small range, right? So we just align with this aligned assumption with the observations we have made, and then we can show that the marginal probability of the data, or the likelihood of the data, can be approximately to be the likelihood of the data when you use map estimation, multiplying with the ratio between the posterior range and the prior range. So remember, this one is less than 1. Right? Posterior range is quite small, quite concentrated, and the prior range is quite larger. Right? Any questions so far? Okay, and then if we take a look at this and take a logarithm over this data probability, we found that it can be decomposed into 2 terms. One term is the log likelihood under map estimation, right? This is something we are always familiar with. And the other term is logarithm of the ratio between the posterior range and the prior range. And we can make even like a crazy assumption that if W is like high dimensional, because the weight vector would be like m dimensional, right? In m dimensional space, we'll also assume the posterior will be concentrated on some small cube, hypercube. And each length of each side is also this small length. Right? And obviously, the prior is assumed to be concentrated a very large hypercube, and the length is proportional to this. Right? And then, given m parameters that assume the same ratio, we can analyze that the log probability of the data is approximately the log marginal likelihood multiplying with m. Remember, because when we calculate the error or the volume, we need to take the power of m, right? When you take logarithm again, you multiply m in front of it. So this is the model evidence, log model evidence, given some specific family of models. So we can see that the log model evidence is determined by 2 terms. One is from the likelihood, meaning that if you use this model to explain data, how good your model explains, right? And the other terms actually relates to the properties of the model itself. Why it relates to the property of the model itself? So the more parameters your model have, what will happen to this term? What? So remember, this one is much smaller than this one. So this ratio is less than 1. So this logarithm is less than 0. So that means when you increase m, you end up with decreasing the whole model evidence. Right? So what does it mean? It means that, okay, the more complex your model is, the more harmful to your model evidence. But as we know, the more complex model you have, the more likely that you will better fit to data, right? So now you see a trade-off, right? So I know some model is like very complicated, like with like millions parameters, even billions parameters, like 125 layers of neural nets, right? It can give you the, suppose this is a training error or whatever, right? It can goes to a very, very large, I mean the log likelihood. Right? At the same time, it hurts this term large, and finally end up with some intermediate model evidence. Right? So there's a trade-off here. On the contrary, if your model is quite simple, you might not fit the data that good, but this part is small. Right? And overall, you will end up with a good model evidence. So in practice, if you want to select models, we can simply maximize the model evidence. And here is just one conceptual figure to show we actually choose some kind of trade-off. Right? So x-axis represents the distribution of the data. Giving you some data, you want to say, and you want to say how those data are allocated in some space, right? And y-axis represents the evidence of the model for this data. So suppose we choose some data set like D0, we see that we're going to choose M2 here, rather than M1, rather than M3. So this is the procedure, typical procedure to select model. Does it make sense? Okay. So these are about like how do we compute the predictive distribution overall, right? So suppose your model is determined by some specific hyperparameters. So in our case, the Bayesian regression problems is determined by alpha and beta, as you just mentioned, right? Alpha and beta determines the Poire variance and the noise variance in the likelihood. Right? You can imagine that one specific choice of alpha and beta represents a particular model. That's why I tell you in the figure we just mentioned, you fix alpha beta means that I fix one particular model. I observe that. If you want to look at, okay, how does alpha and beta change will affect behavior, that's another story. Okay? So if you want to take into account the model in computing our predictive distribution, the full Bayesian treatment will need you to compute the posterior distribution of alpha and beta as well, the hyperparameters beta. Or in other words, alpha and beta, each one pair of beta determines one specific model. You have to compute the posterior distribution of the model. And given one model, you compute the distribution, posterior distribution of the model parameters W, given observation T. And then you compute the prediction. And you do the average over all the families of all the models in the family and all the parameters within each model, you get to the full predictive distribution. That's what we want, ideally.
So in the previous slide where you introduced this, so it was conditioned from the training data and alpha and beta. Right. So now when you get the predictive distribution, it's not being conditioned on any alpha and beta. It's a generalized.
You mean calculate the predictive distribution?
Yeah.
No, it's conditioned on observations T. You need to compute the posterior distribution of the models.
So the earlier expression, it was conditioned on alpha and beta. So that was.
Oh, for that, okay. That has nothing to do with this. So it's just some specific value of alpha beta. You can choose like randomly.
So that is a generalized one. So it's not nowhere conditioned on any one.
No. There's just some say. I can just show you one case that when I choose a particular model with alpha being 1, beta being 1, that's the typical behavior. Of course, if you choose alpha equals to 2 and beta 2, you might have same trend but different curves or whatever. Right? Any other question?
Are you saying that the parameters to the normal distributions for the weights have distributions themselves?
Yeah.
Okay.
So here I want to differentiate alpha and beta with the model parameters W. So W is associated with some specific model. They are random variables, right? And then alpha and beta determines the specific model you want. So you want alpha equals to 1, beta equals to 1. Okay, you determine one model, but I do not know the model parameters W. I still need to calculate posterior distribution to determine that, right? But right now, if I want to consider all kinds of models into our predictive distribution, we need to take into account the posterior distribution of alpha and beta, because this is actually the posterior distribution of the models. Does it make sense? Okay. And this is ideal. This is something like ideal Bayesian should do, but in practice, this is often not feasible. Because this posterior distribution and the posterior distribution regarding the hyperparameters is even trickier to compute than the posterior distribution of the model parameters. So in practice, we want to find a trade-off. We want to compromise. Right? So how do we compromise? We only marginalize our model parameters. And we fix alpha and beta. And then to calculate this posterior distribution given some alpha and beta. So now you can say this. Now this predictive distribution is parameterized by alpha and beta, right? Now we maximize this distribution to find out the best alpha and beta. That means we maximize the predictive distribution to select the best model, right? Because alpha and beta index one specific model. Does it make sense? Right. This is called empirical base, or type 2 maximum likelihood estimation. So type 1 means that, okay, I'm gonna maximize W. And if you want to select a model, at the same time, I probably can join the maximize alpha, beta, and W. Right? But type 2 means that I want to remove the effects of W. I just integrate out W and just maximize the predictive distribution with respect to alpha and beta. This is called a type 2 maximum likelihood, or sometimes called empirical base. Any questions so far? Yeah, those are like different from what we have normally mapped before. Maximum likelihood estimation, map estimation, like maximal map estimation, and blah blah blah.
So going back to type 1, so if those parameters also have distributions, how are their parameters decided? Their prior parameters?
Yeah, that's a good question. So one way is that you put an uniformity prior over the hyperparameters, meaning that I do not associate any preferences on them. So this is called hierarchical Bayesian model, right? You first sample the hyperparameters that determines one model, and then given that model, you sample the model parameters, and given the model parameters, you sample the observed data, right? But you cannot have like infinite hierarchies. At the top level, you're going to be assigned an uniformity prior. Any other question? Okay, so maximizing model evidence can take the same kind of effect as the cross-validation. Because when we talk about model selection, the most commonly used straightforward methods to do the cross-validation, right? I like split the data into like training and test part, and I use training to test, and you test to evaluate and do it multiple times, take the average as the evaluation of this particular model. I do it for multiple models. I pick the one with the best performance, right? This is cross-validation. Everyone knows. But in Bayesian world, you can also achieve the model selection by maximizing the model evidence, right? So we can say how the results are consistent with the generalization performance, right? So this is the polynomial regression case, right? So this figure we have seen before. like when you increase the orders of the polynomials, your training error keep decreasing until 0. But at some point, your test error drops dramatically, right? And if you look into the model evidence for different choice of M, you will see when you increase M, your model evidence actually decreases, right? And your best is around something, I believe it's 3. This is consistent with what we have observed previously. We said that if you take M to be 3, your learned curve is much more reasonable. Yeah, so I have finished the linear models for regression, and I guess we don't have time to cover the linear models for classification. So let's continue the discussion next week. So we start already today.